Welcome to this lecture. Today we will start a new module, and this module is on these functions of random variable. So, why this is important is that so far we discuss about the different properties of one random variable and their probability distribution, their cumulative distribution function and their different properties. We have seen different standard probability distribution which are most useful in civil engineering, and what we are going to discuss in this module is the functions of random variable. So, if we are having one random variable and if we can relate that particular random variable to the another one in terms of some functional relationship, then if I know the distribution properties or the probability distribution of the random variable, then we want to know the properties, the probabilistic properties of the dependent random variable. So, for example, it is a y equals to gx can be the treated as to be the one general function. Now, what is known to us is the all the properties of the x is known, and we want to know the properties for the y. So, this is the basic theme of this module, and in today's lecture we will start with the fundamental theorem, and that fundamental theorem in the subsequent lecture we will show that for the different methods for which we can understand the different properties of that function. So, our this module name is this functions of random variable, and is in this particular lecture we will discuss about the function of single random variable. So, here the single, what we mean is that only one random variable is there for as the independent random variable, and that is having some functional relationship with the other dependent variable. So, that function, once we know that functional form, after knowing that functional form I want to know their different properties. Now, say this one is in fact what we can relate it to that. For example, in the previous lectures we have seen that normal distribution, and from there we have seen the log normal distribution. So, that what we have seen is that y equals to log x if I take, and if I say that this log x, that is a y, is the normal distribution, then that x is the log normally distributed. So, now the reverse function will be that x equals to e power y. Then if this relationship is known and I know the what is the function of this normal distribution, then by exploiting the properties that we are going to discuss, then we will know that what should be the properties of this that log normal distribution. So, here what we mean the properties is that we should first know that probability density function. So, knowing the density function of one random variable, I want to know the density function of the another random variable which is having some functional relationship with this random variable. So, why we are using the word random variable is that we know that this the random variable is a function that we discussed at the towards the initial lectures of this course. This random variable is a function which maps the relation from the outcome of a particular random experiment to some number on the real line. So, that is a functional dependence while we are defining the random variable we know. Now, when we are defining another function based on the random variable, that function is also a random variable. So, so our focus today is to know the distribution properties or the density of those functions which is developed based on the known random variable to us. We will go like this. First of all, we will discuss the functions of random variable. Basically, the functions should have some characteristics, some should have some properties before we can say that this is a function of the random variable, because that random variable, the functions are also the random variable. So, that condition should satisfy we will discuss that one first, and then we will see some fundamental theorem how we can determine the probability density function of such functions. There are three different methods, that method of distribution function, method of transformation, and method of moment generating function, which are all these three methods are basically based on the fundamental theorem that we are going to discuss now, and also the method of the characteristics functions are there, we will be discussed in this lecture. So, based on this fundamental theorem and with some additional condition, we will see that. So, if we understand that fundamental theorem first, then understanding of this one will be very easier. Mostly these methods will be covered in the next lecture. Today we will understand that fundamental theorem. So, first of all, what we discuss is that there any random variable which is denoted as x is a function that map the outcome of a random experiment to a number on the real line. So, random variable itself is a function that we know. Now, this is having a functional relationship with some other. So, now from the x what we are having is the gx. Now, gx which is the y equals to gx. Now, this gx is also a random variable. So, we want to know the properties of this y when the properties of this variable x is known to us. So, the definition of this functions of random variable is states like this: a function of single random variable. Here we are discussing about the single random variable. Similarly, we will see the properties in the subsequent lecture for this multiple random variable as well, where there will be more than one random variable and their functional relationship with some other random variable. So, here the functions of single random variable x is a composite function of y equals to gx is equals to gxj with the domain set S of the experimental outcome. This is taken from Papulas and Pillai. Here this j is the outcome of that random experiment. Now, we know that all the outcome of this random variable is mapped to the real line through this random variable x. So, we know, so this is generally is going to generally stating a specific number, and that number is here. So, and this gx, so g is a functional form, and I want to know that after taking this function what is their properties. So, this is the function of that random variable x which is known. Now, for an outcome j, so we are taking one specific random experiment, and just one specific outcome of this j is, if it is taken, then we know that this xj, when we are taking that random variable, this is basically is a number which is mapping from the sample space to the real line. So, this xj then is nothing but a number. Now, if this xj is a number, then that this gxj, that is after I take that function, that gxj will be the another number which is specified in terms of that original random variable xj and its that functional form, which is gx. So, if we just see it here, so this is that function, this is that random variable axis. If I just say that this is the axis x that is known to us. Now, there can have some so this function can be general like this, that which is your gx. Okay. Now this function is known to us. So now, so for the anything, any number, what we are getting is here is that functional dependence. What we have to see is that based on this change here in this so y equals to gx, so we can just write that this is y equals to gx. So in the a change in that dependent variable, I can say that y. So what is the change, what is the properties that we can investigate from the original random variable x. Now from the, if I say that I know the original random variable, that means what we know is that its distribution, whatever may be the type of this distribution, we know. Now for this I have to find out, so for each and every possible outcome of this random variable, which is nothing but, so from the we know that from the sample space, each and every outcome of this random variable is mapped to this real line. And so this, from this one, based on this functional relationship gx and this number, this function is known to us. So this gx is defined, is another number specified in terms of this, both this functional property as well as this number, which is mapping from this experimental outcome to this line. So this is what is specified here. The for an specific outcome xi, for an outcome xi, x xi is a number, and this gxi, that functional correspondence, is another number specified in terms of this xi and this functional form gxi. Now the functions of the random variable, that is y at xi, can be represented at y xi, and value of this number can be taken as y xi is equals to x xi assigned to the random variable y. Now this is important in the sense, now what we are doing is that from this experimental outcome, so this is the specific that outcome xi, that this is that your x xi, and from here what we are going, we are taking this function and to this function gx, and then we are coming to this axis, that is a y equals to gx. And so this one now is, what is that, this corresponds to the outcome of this original outcome of this random experiment xi. So this one is your, now what we are saying is that this is your xi. Okay. So from here now we will see the, if so maybe a very general function is drawn here, so there may be some different roots, and we will see that if we are having the different roots or more than one roots, to be in general, if we are having the more than one root, then how to handle this property, that we will see, and that is basically our motivation for this fundamental theorem. Later on we will proceed to the special case where these functions will be defined in such a way that there is only one-to-one correspondence is there. So this one-to-one correspondence means that whatever the outcome of this original experiment, that outcome of this experiment, random experiment, is there, that is having a particular number that we know, and from here when we are going to this function, this relationship is just one-to-one. For a specific value of x, only one outcome, only one possible value of y is there. So that will be the special case. Now today in this lecture, what we are talking about, the general case, there may be means n number of roots for the specific outcome, that we will see today's class. So thus a function of the random variable is a composite function which is y equals to gx, and this number is gx xi, with the domain set S of the experimental outcome. This domain set S means that original random experiment, the outcome of this original random experiment. Now, so what we have to know is the CDF, that is how this cumulative distribution function of the y, that function. Obviously, when we are talking about the function of random variable, that means all these properties, all these functions related to the x is known to us. So based on that, what we want to know is that the cumulative distribution function of y, f y y, for the random variable y, which is a function of x, defines the probability of the event that y is less than y, that means this is a random variable, this is a specific value, so less than y consists of all outcome xi which satisfy the condition that this g of x xi less than equals to y. This is very important, and this concept is very important to know that where we are means which value we should classify as this set, this event set. This would have been more straightforward if we just directly say that it is a one-to-one transformation, but when we are talking about the general case, then we have to find out those subset of the x where this condition is satisfied. We will see that. Now, so for a specific value of y, the values of the x satisfying that gx is less than equals to y from the set Ry, from the set Ry. See, Ry we are now resonating that that the set which is satisfying this condition, that is this is the functional form gx. Now, that gx for all possible value of that x which after having this functional transformation will be less than that specific value y. So, if I want to know that what is this one, this that cumulative distribution function of y, what we have to do is that this is that cumulative distribution of y. So, we have to find out the probability that x belongs to that set Ry which is satisfying this condition, that is gx is less than equals to that specific value y, where we are defining that this CDF, cumulative distribution function, that we will see in this general case. So, just keeping this point in mind, we can say that to satisfy that gx is a function of the random variable x, this gx should satisfy some condition. There are three conditions. This should be satisfied before we can say, because this function itself is a random variable as we discussed. So, just by knowing that just by stating that this itself is a random variable, so this should satisfy some conditions, some three conditions are there, that should be satisfied before I say that this is a function of the random variable. The first condition or the first condition is that its domain, that domain of this gx must include the range of the random variable x. So, whatever the support we generally say, the support of this x is there, that entire support, that entire range of this random variable should be included by the domain of this function gx. Let us take one example here, that if the function is like this, y equals to log x, and this x can have the negative values. Now, if I say that y equals to log x, whenever we are saying that this is the functional dependence and this is that y equals to log x, and while giving the properties of this x, I am saying that x is a random variable with the range that say for example the -5 to +5, or some negative values are there for this x or for its support. Then this y remains undefined for such values. So, for this negative zone, this obviously this y cannot be defined. So, thus in such cases when this x can take the negative values, this logarithm of the random variable is not acceptable. This is also true if I just take the square root. So, y equals to square root of x, and we are saying that x is having its support towards the negative side as well, then those functions are not acceptable. Then in what condition this will be acceptable? If I say that this x is a random variable with its lower bound at 0 or some positive number, then I can say that okay, fine, no, this functional form in terms of this function of this random variable is acceptable. So, the domain of the function should include the entire range of the x, that is what the first condition is that. So, its domain, the function domain of the function g x must include the entire range of the random variable x. The second condition is that it must be a Borel function. Now, you know that when we are talking about this Borel function, we have defined it in towards our initial lecture that it should be the set, its union and the all possible unions and the intersection are also inside the set. So, if you recall that if the events a1, a2 up to an belongs to a particular field of set F, then it is called as the Borel field or set if the unions and intersection of these sets means a1, a2 up to an also belongs to F. So, then we say that this is a Borel set. So, the second condition of this function is that it must be a Borel function. This is just to satisfy that this one, after taking this function, that is also a random variable. So, properties of this random variable should be satisfied. So, that is why it comes as a Borel function, so that we can take that unions and intersection. So, which states that for every y, the set Ry satisfying that gx less than equals to y, this must consist of the union and intersection of a countable number of intervals. This requirement is to satisfy that this y less than equals to y is an event. And the last condition, which we also have seen that for the random variable, is that this random variable, that is a gx, at plus minus infinity, its probability at plus minus infinity should be equals to 0. So, the event gx equals to plus minus infinity must have 0 probability. So, once this three condition is satisfied, then that function can be called as this function of a random variable, and then we will see if this kind of functional correspondence is there between this x and y, then how we can get the density function of this random variable y, which is having a functional relation with that x. So, obviously, the all these properties which is required for this random variable x is known. Now, if I say that this f(x), that is the probability density function of the random variable x is known, that means I know everything about this its distribution. So, this function is known, this density is known for the x, and this relationship is known, and this function satisfies those three requirements to be a function of random variable. With these things in hand, we have to determine the fyy, which is the probability density function of y. Now, to find the fyy for a specific value of sorry for the spelling mistake, this value of y, then this y equals to gx is solved. Now, while calculating this density function for a particular value of y, I take that particular value of y, fit it in this equation, that is this y is known. Now, this gx, so x is now is unknown. So, we have to find out that what is the value of x. Now, as I was telling that if there is the relationship is say 1-to-1 relationship, then there will be only one root. So, 1-to-1 relationship means for a specific value of y, there is only one value of x and vice versa, but here that we are making it the general. So, this y equals to gx if there are having the n real roots of this equation, say that x1, x2, xn. That means what we are telling here is that for this kind of function, if I just take for a specific value of this y, so this is the specific value of y. Now, I have to get that what are the different points that it can that the root of this of that equation. So, the first root is here, second root is here, third, fourth. So wherever it cuts that function, we will get that these are the roots. So if in general case we say that there are such n such roots are there, which are x1, x2 up to xn, then it can be shown that this fy, the density of that of this random variable y, can be stated like this. So this fx, value of this fx at x1, fx at x2, these are the density function of x evaluated at those roots, divided by this g prime x1 its mod, g prime x2, g prime x3. So this is the derivative. So in the mathematical term, you know that g prime x is the derivative of this function x, or you know that this derivative is nothing but it is the rate of change of g at that point x1, and we are taking its mod. So we will just show that whether it is increasing or decreasing, it should not matter. So this fx at x1 divided by gx x1 plus, similarly for all such roots we have to take the summation of that one will give you the density function of y. Now we will see how this relationship is holds good. This proof is taken is for the general case, and here we have taken that 3 such roots. So basically we are assuming that at a particular value of y we are getting the 3 different roots. So these 3 different roots, how you can say that for a specific value of y, so this is the location of this y, and if I just go through this one, so these are the 3 specific values of that root. So this is, as it is shown here, that x1, this one is shown as this x2, and this one has shown it to be the x3. So it will be more clear if I just redraw it one after another. So this is my that y, location of y, and this is the x, and x the CDF, that is PDF, that is fx of x is known, and let us say that this fx of x is like this. Now for this one, this is actually referring what we are, the first root is the x1, this is your second root x2, and this is your third root x3. Similarly, depending on this function, there may be n numbers of roots like this. So what we are basically trying to do here is that this y, if I take a small area, means small range from y to, say this is said the dy, so this is the increasing side. So if I just take that, this one is that, what we are saying is the y plus dy. So what we have to find out that from this y to y plus dy, what are the ranges that is being covered for this x. So if we can identify that, then that is basically giving you the set of that ry, that just what we defined few slides back, is that is giving you that what is your that set for ry. Then we can calculate its that density. So then at this one, what will happen, this, if I just draw another line here, it looks like this. So this is your, what I will say, that this is now this location is now your that x plus dx1, this is your x plus dx2, and this is your x plus dx3. Remember that this direction means when it is going from y to y plus dy, from this point to this point, this is coming from x1 to this one. So this, that means that dx1 is your negative. Similarly that dx similarly that dx 3 and this dx2 is your positive. Okay. Now what we have to get here is that these are the set that we are talking about, which is covering in this for this y2 y1. These are the three areas which is that changing for the random variable x. So this is what is explained in this figure here. So now if I want to know that what is this fyy, then this is nothing but the probability of this y to y plus dy changing to this one. Now it suffices therefore that to find the set of the values of x, which is my ry, such that this condition is satisfied, that is a gx, which is nothing but the y, is from the y to y plus dy and the probability of that x in this set. So probability of that set in this set of this x means what is here the shaded area here, and we have shown there that these are the three areas that the probability should be equal to this probability, which is the cumulative probability from this which will form the cumulative density from this y to y plus dy. Now there are these three sets are like this, which we have identified and shown in this one. The first set consists of this three interval from this x plus dx1 to x1. This is the first set. Then the second set is from the x2 to x2 plus dx2, and the third set is the x3 plus dx3 to x3. So as we told that this dx1 is negative, dx3 is negative, and dx2 is positive. So that's why how this movement. So from this y it is going to here. So that from y corresponds to x1 and y plus dy corresponds to this point, which is, that's why this dx1 is negative here. So from coming from this point to this point. Now yes, these points we just told that which one is positive and which one is negative. So from this it follows that this probability of this y in between this zone, the y to y plus dy, should be equal to the probability of this first set, which is x plus dx1 to x1, plus the probability from the x2 to x2 plus dx2, plus the probability x3 plus dx3 to x3. Now you can extend it if there are n roots. So this kind of n different sets will be there that you have to add up. Now this right side of this one, the right side is equals to the shaded area in the figure that just now we have shown, that this is the these are the shaded area of this the probability. Now since this this probabilities, that is the probability of x1 plus dx1 less than x to x1, it is the density function at x1 multiplied by dx1, that small change from that point. So basically this is how we are calculating the area, and area on the PDF you know that is nothing but the probability. So what if you just refer to this one? So this area, this area we are talking about. So this area, how to calculate this one? So we have to see that what is its height multiplied by this small infinitesimal small area, is that this is that fx. So I am just talking about this area. So this is that value of this function at that point x1. This one is multiplied by this dx1. So dx1 is this this small length. So this is basically giving you this area. Similarly, if I want to know that this area and this area, so if I just want to add up, so this area will be then fx, the same function, value of the same function at x2 multiplied by the rate of change, the multiplied by this small infinitesimal small area, which is dx2, plus this area now fx at x3 now multiplied by this small length dx3. So this 3 is the total area of this one, which is the probability. This should be equal to that probability from this y to y plus dy, that is y less than y plus dy. So that is what is explained here. So these are the 3 different areas, and 3 different areas are shown like this. Now this one, this small this length can be this dx1 again can be defined in terms of this. So at this dx1, this is the dy g prime dx1. So the rate of, this is the rate of change of that function, and this dy is the what is the small change in that y. So this is relating to this one. You can refer it to this one, that is this length. What we are talking about is that dy, referring to this one, if I just say here that this is your dy dx1. So this is your nothing but the rate of change of y at x1. So this is that g prime at x1. So this is how this y is changing for this function at that location x1, and this is simply for followed that from this infinitesimal length where that dx1 will be equals to dy at x1. Similarly for this other locations as well. So these three these 3 things are shown here. The dx1 equals to dy slash this g prime x1. Similarly dx2 at x2, this rate of change of that function at x2, and this dx3, there is a rate of change of that function at x3. So now if we just take this equation, that is, this is the probability, this is the total probability for the function y, which is again what is that? This is the probability density multiplied by the small length, which is dy. So this one, the density multiplied by this small length is equal to this probability of y to y1. You know that. Now from each and every such subset, we can just replace it by this one, following this expression that we got, that is fx x1 so this dx1 is replaced by this one. So dfx x1 dy by this gx g prime x1. Now you see that when we are talking about this g prime x1, whether it is going from this direction to this direction and this one to this one, is doesn't matter, as long as we want to know the total area. So once we are knowing the total area of this one, then what is happening is that we can take as well that mod, just to avoid that if there is something that negative side. So that's why this mod is taken. For the positive side, no effect. For the negative side, we will just get the absolute value of that rate of change. Now, so this is for that at x1, which is the first root, and this is similarly coming from the second subset, which is for this at x2. Similarly, for if there are as many roots are there, so like this. So this immediately the next step we will get that fyy, that is a density function for the y, is equals to fx x1 by this means just a summation of these ratios. So we are getting this form for this one. So this is known as this fundamental theorem for the determination of the density function of y when the density function of the random variable x is known. We will just take one small example. This is purely mathematical example. Before I come to the civil engineering example, I will show that one. So suppose that here that one function, that is the density of a function, is given as 2x by pi square. So if this function is given, then this it is from 0 to pi, this support is from 0 to pi, means you can also check whether this what are the condition for the for a function to be a PDF. So whether this over this support, whether those conditions are satisfied or not. The first condition, we know that it should be greater than equal to 0. So as long as it is between 0 to pi, all these functions are greater than 0, and you can just follow a simple small integration from 0 to pi of this function. You will see that it is coming to 1. So this is a valid PDF, but that is not our focus now. What we want to know is that, what we are interested to know, that if there is a relation like this, that is y is equals to sin x. Now how to know that what is the distribution for this random variable y? So we have to determine that fy y. So this probability of x falling outside the interval that 0 to pi is 0. So obviously, because we have given this range, the range of the support is support x. So why we are telling is this one is that if there are some roots, while we are calculating the roots, if there are some roots outside this zone, obviously that we have to discard. And you know that sine function is infinite, and if I just take a specific value here, so it will look like this. I think the diagram is there on the next slide. Yes. So this is the sine function, if you see, and now this one is from 0 to 1. Now if I take any value between this 0 to 1 y, just remember that the fundamental theorem, if I take any value of this y between this 0 and 1, and if I take its, if I see its roots, and there will be many roots, but we have to consider that only the roots which are in between this range from this 0 to 1, over which that x is defined. Now we have seen that x is defined from 0 to pi, so that there is a possibility that only two roots x1 and x2 should be considered. Now we will go step by step on this one. So as this is the range, so the probability of y equals to sin x falling outside the interval 0 1, also fy is equals to 0. Now let us refer to this figure again. So for any value of y 0 to 1, the equation has an infinite number of solutions starting from x1, x2, x3 like this, from it is x minus 1. We are just giving some numbers. So these are the number of solutions where the principal equation is this. Obviously you have to just put one, any value of y, and this x1 you will get this solutions we will get. Okay, before that, one more thing, this plot is showing the density function of x, that fx of x, which is a linear function starting from 0 to this up to this pi. So you can see once again here that at 0 fx equals to 0, and at pi fx is equal to 2 by pi. So this is a linear function. This is a linear function between 0 to pi. Now, so from the symmetry in this figure B, that is this one, you know that now we are considering only this part from 0 to pi. So now this is symmetric. Now you know that if it is symmetric, then this x2 we can get that x2 is equal to pi minus x1, and so on. And also that dy dx we have to calculate. This dy dx, that is the rate of change of y at any value x, is cos x, which can be written as this 1 minus y square, sin 1 minus sin square x, and sin x is a y. So there is a function relationship. So this is square root 1 minus y square. So therefore at any root, irrespective of how many roots are there, at any root, this mod of this dy dx is square root of 1 minus y square. Now we are using the same equation that is developed, that is for this n numbers of root. This fy is equals to fx x1 g prime x1, fx x2 g prime x2, plus this way if we go on, and here there are only two roots. So this fy1 is that the summation of this 1 by y 1 minus y square, which is a mod of dx dy now, and this fx xi, which is between this y is between 0 to 1. Now you see that this fx minus 1, so these are just the notation we have just used. The minus 1 means what we are referring to this one, this solution, which is below which is less than 0. So this one, this point x1, and this x3 means the next one, this solution. Apart from x1 and x2, what we are meaning here. So this all other apart from the x1 and x2 is equals to 0, because it is outside the range, except that for this fx1 and fx2. So these two things should be added. So fx at x1 and fx at x2, that divided by this, because this is same for both the things. So the square root 1 minus y square. Now we just simply put these two functions here, the 2x1 by pi square, 2x2 by pi square. So 2x1 minus pi minus x2 divided by pi square 1 by square root of this y. Now you put this value, then we will get that functional form like this, that 2 by pi square root 1 minus y square. So this we know that x2 is, we have shown that from the symmetry, x2 is that pi minus x1. So these things get cancelled, and we get the form that 2 by pi square root 1 minus y square, and this is for the range of this 0 to 1, otherwise it is 0. So this is the distribution function of this one. So if everything is okay, if this calculation is okay, as this is also the PDF, that probability density function of another random variable. So all the condition that we are defining should satisfy by this new PDF as well. So it should be greater than or equal to 0 over the entire range, and the integration over the support should be equals to unity. So that you can check yourself, that whether the function that you got, whether those are satisfying or not. So this is the presentation of this, how this PDF looks like here. Now we will take one example here, which is related to the strain energy. And the force. This is denoted as S, and this is denoted as U. Now, in a linearly elastic bar, these two variables are related, that is the strain energy is equals to this is proportional to the square of this force. So, let us say that this is a constant and a square. Now, this constant basically is related to the property of that bar, say its length, its cross sectional area, its modulus of elasticity and all. Now, if we know the probability distribution of this S, whether we can calculate this U, that is what we have seen just now, that we will see. Suppose that this S is having a normal distribution with mean 0 and standard deviation 1, that is, it is a standard normal variate. So then what is the distribution of this U, that we will see in this example. So as we have seen that these two random variables, that is U and this S, are related through this equation, U equals to some constant multiplied by S square. So we can express that this S, that is a, now these two are random variable, that is why it is capital. So this S is now can be expressed that as the two roots, we will have one positive and one negative root will be there, and this is that U by that constant C. Now, so thus if we from here we can see that this ds du is equals to, we can do this and we can get that 1 by 2 square root of u, that constant C. So this is, and if we take that modulus of this, that is the modulus of this derivative, that is which is also known as this Jacobian, is equals to your 1 by 2 square root u C. Now to get the density function of that new variable, which is u, which we can write like this, which should be what we know that at all the roots we have to find out what is the distribution of the other variable, that is here is the s, and at those roots only. So, the one root is that is your square root of u by that constant c, and the other root is that your f s, where it is the other one, that is the root is square root of u by this one, and this multiplied by this absolute value of this derivative ds du. So, if we just replace this one in this expression, what we will get that, so this we can just write one by 2 square root u c. Now, we can put this one from this standard normal distribution, that is 1 by square root of 2 pi, and this is that value x, and exponential power minus half of this square, and again this value, and after doing those steps in between, we will get that final thing will come like this, 1 by square root of 2 pi, that constant u exponential of minus u by 2 c, and here this u is greater than equal to 0, which is the support of this new distribution. So, we have seen that this h, when it is a standard normal distribution, then the square of this one is giving you a new random variable, which is basically a chi-square type distribution with 1 degrees of freedom, and its support is u is greater than equal to 0. So, what we have learned, the fundamental theory we have seen from how to determine the density of this equation from one known random variable, and its if there is some functional dependence, and we have seen that what are the conditions should be satisfied to be a function of a random variable, and once we know that functions, then how to determine the probability density from the fundamental theorem we have seen. And in the subsequent lectures, we will see some special cases. If there are some one-to-one relationship, then what will happen, and there are some other methods called method of moments, method of which is also similar to the method of characteristic function. We will discuss in the next lecture. Thank you.